Thanks, everybody. Thanks, everyone, for coming. Such a great to have a huge audience. I hope everybody can see and participate. First thing is I do have a repository, a GitHub repository with all the course materials. Don't feel pressured to be all hands-on with this stuff, but if you want to, you can clone it and run it. It's basically for Jupyter notebooks that I'm going to go through. But I don't really have any hands-on exercises, but as you know, Jupyter notebooks are very hands-on themselves, so you can get in there and play around a little bit. But I'm going to work through those four during the course of this tutorial, and if you cloned it previously, you might want to do a Git update. I did a little bit of bug fixing and typo correcting during lunch, so there is a little bit of new stuff in there, but otherwise we will get going. In terms of questions, feel free to ask clarifying questions during the presentation. I'm happy to answer them, particularly if it helps you understand the rest of the material. With 90 minutes, I'm going to try to hit sort of 20 minutes per notebook, hopefully leaving us some time at the end, but I'm not terribly good about staying on schedule. So we'll see how that goes. First thing is this big enough for everybody? Probably no. Oops. Hold on. Good? Good. Okay. The URL is my last name / MCMC _ PyData _ London _ 2019. Cool? So as the title suggests, I'm going to focus on Markov chain Monte Carlo, which is one aspect of Bayesian statistics, namely a numerical method for fitting Bayesian models. But I also noted, when I introduced the talk in my abstract, that I don't expect anybody to have statistical background. So I'm not going to focus on theory in this tutorial, but I am going to start with a little bit of it, just to give those of you who are very new to Bayes the opportunity to understand a little bit more about it. But we're going to focus on the computation and how to actually specify and fit those models using the software. Okay, so I'll skim over a lot of theory. At the bottom of each notebook, I've got to learn more sections, which have links to either books or relevant papers, and you can dig in a little bit yourselves. And I'll be here through Monday if you have any questions as well. So, starting at the beginning, what is Bayesian analysis? How many of you have learned about Bayesian statistics at some point during college? Holy cow. Okay, it's much better in Europe, it seems, than in North America, because in North America, it typically doesn't happen. I have 4 college degrees, and I only took a Bayes course in one of them, mostly because they generally weren't offered. So it could be that I'm just old. But this may be just review for a lot of you. But the definition of Bayesian statistics I really like is Andrew Gelman's definition: practical methods for making inferences using probability for things that we observe and about which we wish to learn. So the idea is, we're building probability models here, and we're motivated to do that a lot of the time because they can be more robust, because they account for general uncertainty from a number of different sources. So the key is that all conclusions from Bayesian analysis are stated in terms of probability. So it's probability in and probability out. So these probability statements are what you get. So a little bit of notation: theta is anything that's unknown. So this could be a regression parameter. It could be a rate. It could be a mean. It could also be something like a predicted future observation or missing data. That could also be theta. And then we're conditioning on some data, some observations. So theta given y. Things we don't know given things that we do know, or at least that we observe. All right, and there's some benefits to you, the user, by adopting this approach. One is ease of interpretation. So most people have a pretty good sense of what probabilities are. I currently work with baseball players and coaches. I used to work with doctors, physicians, and other scientists. And even though none of those folks are statisticians, they all have kind of an idea of what probabilities are, although they can certainly be misinterpreted. So you can really easily interpret these models, or more easily, and it makes it a nice way for summarizing uncertainty. and it makes it really easy to calculate various summary statistics. All right, so Bayesian, you may be wondering what's the difference between Bayesian statistics and classical ones, or the sort of statistics that a lot of you may have learned in school. Well, with the things that are in common first with any statistical paradigm is that you have some unknown quantities that you're interested in learning something about. That's the thetas that I showed you previously. Some data that you've observed and hopefully have information about the things that you don't know. And then we link those together with a model of some kind. And that model can be anything from a statistical test all the way to a regression model or a machine learning model. But that's where the similarity ends. So if you're a frequentist like Ronald Fisher here, you view the world in a slightly particular way. So the idea if you're a frequentist, you consider your data to be random, that they were generated by random processes. And each time you go out and observe the world, you'll get different values. And so that's the thing that we're going to model. And then your model parameters or your unknowns are the things that are fixed. So they're fixed and we condition on them. So this is kind of how a frequentist thinks. Probability of your data given some values of parameters which are unknown. And so if you're a frequentist, what you do is you spend most of your time coming up with estimators for things. So estimators for those unknown quantities. And so for example, a simple example is binomial proportions, right? So the example here, if you're estimating if you're if you're interested in global health or disease, something like autism spectrum disorder, you may want to know the prevalence in the population, right? The proportion of people in the population with that disease. And so you might observe a certain number of them, N, and Y of them have the disease, and so you estimate a proportion. And it's an intuitive way to calculate that, but there's a reason that you choose this particular estimator. It's got properties, right? It's unbiased or minimum variance or various other things. And so every time you have a new problem, you've got to come up with different estimators for things. If you're a Bayesian, like Tom Space, you sort of see the world differently. You view the data as being fixed. They may have been generated by a random process, but once you've collected them or observed them, they're static, right? Every time you open your notebook, the same data are written down. They don't change. And so because they've been observed, we're gonna condition on those. The model parameters or any sort of unknowns that you're interested in, they may not be random, they may be fixed in principle, but what we do is we use probability to characterize our uncertainty in those values. So they're sort of random in that sense, in that we don't know the values of them. And so this is the same quantity that I showed you above, probability of the unknowns given the data. And so sometimes more in the past, Bayesian inference is referred to as inverse probability because you're reasoning from observations to parameters or from effects to causes. Okay, and Bayesians, other nice thing about being Bayesians is that you don't have to be good at coming up with estimators for things because there's only one estimator in Bayesian statistics, and that's Bayes' formula. So here's my obligatory equation showing Bayes' formula. Okay, and so the thing that we're interested in over on your left is the posterior probability that I've showed you already. And the way that we get that is we combine some information from our data in terms of what we call a statistical likelihood. And notice this is essentially what frequentists use, right? And some estimate of what we know about the unknowns before we collected the data. We call this a prior. So we have the world before we did our experiment or observed some data. We add data to it, and then we update what we know about those unknowns about theta. And then there's this pesky normalizing constant, which causes all sorts of problems that we'll come talk about a little bit more later. Okay, so easiest way to demonstrate some of this is with a simple example. So I'm going to go about introducing both Bayesian inference and PyMC using a relatively simple example. So a statistical hypothesis, right? Sort of thing you'd get in classical statistical applications. And in a classical sense, what you would do is you'd come up with a hypothesis that you're interested in, and then some alternative to that, a null hypothesis, essentially the world without that effect that you're trying to estimate. And you would typically come up with some sort of test or test statistic that would determine whether or not you can abandon that null perhaps in favor of your alternative. And the reason some people become Bayesians is they don't really like that approach. We're not always trying to test things necessarily, but we shoehorn things into statistical tests. It involves a lot of arbitrary decisions like which test to use, which null hypothesis to test. Sometimes those null hypotheses are really trivial and easy to reject. And then the level at which we declare something to be quote-unquote significant, which causes all sorts of problems, as you may have noticed in some of the statistical literature. What we're going to do instead with the Bayesian approach is still evaluate hypotheses, not necessarily test them, but we're going to use an estimation, right? We don't just want to know is an effect present or is something significant. We want to know how big it is or how significant it is. And so what we're going to do instead is build a model, estimate the things we don't know, and then as a bonus, come up with estimates of uncertainty around that. Okay. And the case study I'm going to use here is this example pops up a couple different times in Andrew Gelman's books. This is a radon contamination study. This is some data collected by the United States Environmental Protection Agency. And they go around measuring radon in different places. Radon is the #1 cause of non-smoking related lung cancer, and it kind of seeps into your house through the ground, depending on where you live. Our house in Nashville, Tennessee has radon contamination, so they've got, plastic all over the basement and a little fan that blows it all out into my neighbor's yard. And so you want to know whether or not these levels are dangerous or not. And so the reason they collect this data is to try to, maybe identify areas in different locations that might be more or less prone to this sort of contamination. So it's a big data set. I'm not going to use all of it. Oh, if you are running this, by the way, I've got all of my notebooks rendered and with all of the outputs, so you may want to clear them. Clear all output. There we go. And what I'm going to do, not going to dig in too much right now about the PyMC side of things. I'm going to just show this to you on a high level to give you an idea of how it works. And then in other notebooks, I'm going to go in a little bit more depth and talk about this stuff. So here's the radon data, and we're going to be interested in a couple of. So we're going to take one particular county in the state of Minnesota arbitrarily, and the level of radon contamination that is thought to be worrisome is, according to the US EPA, is 4 picocuries per liter, I guess that is. And so we want to know, we might want to know, say you're an official in Hennepin County, which is what we're going to look at here, whether the mean radon value for the county is greater than this 4 level, and then maybe the probability that any randomly chosen household in that county would be subject to that level, okay? So this is just pulling out that data, so this is what it looks like. We're going to log transform it, right? These are positive quantities, levels of radon, and so it's sometimes helpful to transform things onto the real line, which is what we're doing here, so we can use things like normal distributions. It makes our life easier, okay? And we want to know, and so log 4 is right around here. So it looks pretty close to the mean, but there's maybe some uncertainty about that. Okay. All right, so what we're going to do is follow the Bayesian workflow. And the Bayesian workflow is really kind of a 3-step process. There's lots of sub-steps to each of them, but in general, what you do first is you specify a probability model, right? So Bayes formula that I showed you before, you want to put everything that you care about that's relevant to the problem at hand into that form. And typically what that involves is throwing a probability distribution around everything that's observed or unknown, and then relating those to one another probabilistically. Okay, so you're making some choices about which sampling distribution the data have, right? So I already hinted at that here, right? This looks sort of normally distributed, so I might use a normal likelihood. That's the data, that's the information. And then what form best describes our uncertainty in the unknown parameters? In this case, right, the mean, the standard deviation, things like that. Okay, those are the 2 most important things. Then once you do all that, you turn Bayes crank, right? You take priors and likelihoods, and you turn them into posteriors. You calculate a posterior distribution. And that can be tricky. They're very hard to calculate analytically. Even though you have a nice closed form equation, it's not always easy to calculate that, as we'll see. But the good news is once you have a posterior, you have everything you need to do your magic, right? You can calculate point estimates for things. You automatically get things like credible intervals, other measures of uncertainty for free because you have entire distributions, right? Remember, our output is all going to be entire probability distributions. And then the third step is model checking. And this is common to all statistical paradigms or both statistical paradigms, but it's particularly important in Bayes because this is all model-based inference. And it's really easy to get a result that looks okay but is entirely meaningless. And so going back and checking the model is very important. What do I mean by checking? Well, if we're using MCMC like we're going to do, did MCMC work just sort of mechanically? Did it work? Did you code your algorithm right? Does the model fit the data? There should be some correspondence between the data and things that's predicted by the model. Are the conclusions reasonable? And sensitivity of your results to some of the choices you make, right? I've told you had to make choices about sampling distributions and prior distributions and things like that, so it's good to go back in there and check. Okay? All right, so what's our probability model? Well, like I've said twice now, we're going to use a normal distribution for our sampling distribution because log radon looks approximately normal. Again, we can go back and check this. They're not written in stone. So if that's our model, then we have kind of two unknowns that are clear here, a mean and a standard deviation. Two parameters define the normal distribution. So we got to make choices about priors. How do we choose priors? Well, it depends on what is the underlying parameter looks like, right? Is it something that's discrete or continuous? What's the support of the variable? Can it take negative values? Does it take really big values and really small values? All those sorts of things. And of course, you may have information that is relevant to the problem at hand outside of what you've observed in your data set that you may want to incorporate. Some consider this a weakness of Bayes that makes it less objective. Typically, it's a strength. Particularly when you're using observational data sets, you want to bring everything into play that you possibly can to get the best possible answer, and that sometimes includes prior information. But you can ignore all that and create priors that are, I won't call them uninformative, though they sometimes are, at least diffuse priors, ones that don't have a lot of influence relative to the data set on the posterior distribution. So in this case, I'm going to choose, for the mean, a normal distribution centered on 0 with a standard deviation of 10. So it's a normal distribution, but it's a really, really wide one relative to our observations. And then for the standard deviation, it's got to be positive. So you can choose things like a gamma distribution or a half, all sorts of half distributions, half normal, half Cauchy, half being the positive half. I'm going to choose a uniform with the minimum being 0 because it has to be positive, and then I pick some value that I know is way too big, that will never be bigger than. The most important thing is not to exclude areas of the parameter space that could potentially be the true value, because then you're stuck. Once you've set a probability to 0, anytime you multiply something by 0, it's always 0. So we got to make sure we don't make that mistake. So those are my choices. And then from PyMC, I'm going to import the things that I need. So namely a model. I need a model to keep things in and some distributions. So PyMC is a very high-level language. It means that basically building models in code looks a lot like you would be if you were writing it down on a whiteboard, and that's kind of the model that we've chosen here. So I'm going to take a normal and a uniform. I'm going to instantiate a model and put it inside of a context manager. So the with statement is a context manager, and what this will do is it will automatically add anything inside that context manager to the model. So you don't have to have all these add statements, which are happening under the hood. Right? So I have a model. I'm going to call it radon model, so I can open it up later and add more things to it. And then here's my normal. Because we're in Jupyter, we can use Greek letters, which are cool. So there's mu and sigma. Looks, again, just like the whiteboard. All right, so those are the first elements. And then we need our likelihood, which is normal. And the mean is going to be our mu that we just defined here, and standard deviation will be the sigma there. And actually, we updated the API to be a little bit more consistent. So not half Greek, half non-Greek. It's all Greek now. So mu and sigma, it'll still work with SD, but may as well update it while I'm here. Okay, there's our model. It's essentially done. I picked a simple model intentionally, and then now we hit the magic inference button, which in this case will run MCMC. So all I've got to do is run sample. I'm going to sample for 1,000 iterations. I'm going to tune it for 1,000 iterations, so it's going to optimize the running of the MCMC algorithm. And it's going to run sample 2 chains on 2 cores. I've got my little pixel book here that's only got 2 physical cores, and so I'm going to make use of both of them. And then we can look at the answer. And so here's the posterior distribution of the mean. And because we have this distribution, so this signifies how much we know about that mean. If there were millions of households in Hennepin County and I sampled from all of them, as that information gets really strong, that will collapse to essentially a point probability, right? You'd be entirely sure of what that value is. But we do have some residual uncertainty here. So it's a mean of 1.3, again, log scale. The log 4 is 1.39 roughly. And so we can say nice things like this, that there's a 16% chance that the true mean is above the critical value, and 83% chance that it's less. Okay? And then, of course, we want to make a prediction, right? What if we take what if a new house is built in Hennepin County? What's its risk of having radon contamination above that level? So we can do something called posterior predictive sampling. So this is where we combine the residual uncertainty from our estimation and the stochastic uncertainty of just random chance sampling, and to make a prediction that combines both of those. So it's essentially more robust than just picking the mean, for example. So I'm going to draw 1,000 samples, and the probability that a given household will have that a value greater than 4 will be 0.46, which is much bigger than 0.16, right? So 2 different questions. Is the mean greater than 4, or 1.39, and what's the probability my house will have contamination, okay? All right, that's the idea. Simple example. I forgot the model checking part, so let's talk about model checking. How do we know that this model's any good? It looks good. It provides sensible results, I think. But how do we know? Well, the simplest way and an effective way of doing that is to use some of those posterior predictive checks. Because what the posterior predictive sampling is going to do is it's going to essentially generate data from my model, right? It's going to generate new data. And so a sensible thing to do is to generate lots of fake data and compare your fake data to the real data. And if the real data looks kind of like your fake data, then it probably says your model's okay, right? This model could have been the true generating model. And that's kind of what we're after. And so that's what we're going to do here. So I've taken, we essentially have 500 estimates. And I'm going to come up with 500 probabilities of a new house having radon contamination above log 4. So that's represented by the histogram. And then here's the empirical one, which is the red line. And your posterior predictive checks could be a lot of different things. We'll talk about that later when I get into model checking in more depth. Okay? And so, boom, if we would be concerned if the data were way out in the tails, right? Then there would be a lack of fit in our model, we would say there. The other thing, prior sensitivity, I picked, a normal for the mean and a uniform for the standard deviation, and I picked those because I've been doing Bayes for a decade or so, but they're subjective choices, essentially. So I'm going to go in and pick different things. So I'm going to pick what we call a flat prior for mu, so it's equally probable from negative infinity to positive infinity, so it's not even a proper prior, yet somehow we're going to get a proper posterior. And I pick a half Cauchy distribution. The Cauchy's got really thick tails. It's like a normal distribution. It's got really thick tails. Also arbitrary, but at least different. And I'm going to leave normal. I'm going to leave the distribution normal. I think that was pretty reasonable. And I'm going to do that again. Run the model again. Here's the estimate. 15.7. Here's what it was before, which was what, 16 point something, right? 16.2. So they're, the credible intervals are the same, et cetera. So it not entirely sensitive to our choices for priors. That's kind of your intro to Bayes. Let's quickly flip over to the MCMC one, which is ostensibly what this tutorial is about. So we've just used MCMC. Now I'm going to dig in a little bit, tell you a little bit about what MCMC does, how to do it. This notebook contains an MCMC sampler coded by hand, again, to give you an idea of kind of how it works. That second step of Bayesian inference, which is calculated posterior, you just glibly go in there and calculate it like it was easy. It's not easy, and that's one of the reasons that Bayes hasn't been taught widely in schools until recently. They're hard to calculate, and they typically require numerical methods. And the reason is while it's easy to talk about turning the Bayes crank and adding prior information to a likelihood to get a posterior, in order for that posterior to itself be a probability distribution, you've got to normalize it, right? You've got to make sure that it integrates to 1. So you've got to have this normalizing constant here. Probability of y, the probability of the data. What is that? It's sometimes called the model evidence, but it's the marginal likelihood. And the reason it's marginal is you marginalize over all of the parameters. So you integrate out the parameters, which is easy if you have one parameter. I can do one-dimensional integration. I used to be able to do 2 back when I was taking calculus in university. I can't do 3, and most of you can't either, probably. So, and the models I typically use will have 10 or hundreds of parameters. So you can't just calculate Bayes in closed form, except for some special cases that we won't talk about here. Most of the time, you've got to do some sort of approximation, and there's lots of approximations. You can do a brute force optimization, which will just give you the posterior modes. Some people are happy with that. That solves some people's problems. Some people use methods called variational inference, where you take another distribution that's easy to deal with and you warp it until it kind of looks like the posterior and you run with that. And that has its own benefits and limitations. What we're going to use is a sampling-based approach. Because the posterior distribution is unknown, it's also hard to sample from it directly, right? We could, if we want to do Monte Carlo, you would take samples from your distribution over and over and over again, and then you can integrate and do all sorts of things. But you can't even sample from it directly because its form is unknown. So if we can't take independent samples, what if we could take dependent samples? Turns out we can take dependent samples. And that's what Markov chain Monte Carlo does. It is a sampling method that generates a Markov chain. And for those of you unfamiliar with Markov chains, what that is something called a stochastic process. And a stochastic process is just an indexed set of random variables, typically indexed by t. Sometimes it's time, right? x1, x2, x3, et cetera. But the important thing is that it's got a particular pattern of dependence. What this says is that the probability of x at t plus 1 given x at t, x of t minus 1, all the way back to x of 0 is the same as the probability of x of t plus 1 given just x of t, the current value. So in other words, the history doesn't matter. Or if it does matter, it's kind of wrapped up in the current value, okay? So it's almost independent, right? It's independent of everything else except this last or current value, right? So if you play Monopoly, a Monopoly game is a Markov chain, right? Probability of being on Park Place in the next turn is only conditional on where you are now. It doesn't matter that you were, in jail 2 turns ago or something like that, right? Markov chains. But not any Markov chain, not just any Markov chain will do. You have to have a Markov chain with specific values. So one part of that MC is Markov chain. The Monte Carlo part is the sampling part. And it's got a sample with a particular pattern. One is that it has to be reversible, right? You can show that, because of this Markovian property, you actually invoke Bayes' theorem to show that, the probability of getting from x going backward, x of t given x of t plus 1, you can solve that through Bayes' formula as well. And you can rearrange it to look like this. So probability y given x or x given y is the transition kernel, so it shows how things move from x to y. And then pi at x and pi at y, pi is the underlying distribution, the posterior distribution that you're interested in. If the Markov chain that you generate satisfies this, it's called detailed balance equation or reversibility, then if you sample from this as n goes to infinity, you will get samples that are indistinguishable from the true underlying posterior distribution, the pi here. Right? Okay, so I wrapped up sort of 2 classes in Bayesian inference in like 10 seconds just then. Again, I'm not going to dig deeply into the theory, but this is kind of what has to happen. Okay, you just have to trust at this point. We're going to come up with Markov chains that obey detailed balance. If we do that and we sample from them, then we will get a Markov chain that converges to the true posterior distribution. Okay, that's kind of the punchline. And there is a number of algorithms that satisfy this, that generate such Markov chains. So there is an A algorithm called MCMC, right? It's a class of algorithms, right? There's no birds called bird. There's just robins and kites and other things, right? Same idea. The sort of most general, most popular algorithm, I guess, is something called Metropolis-Hastings. I'm going to go through Metropolis-Hastings right now and kind of give you an idea of how this works. It's a pretty straightforward algorithm, actually. The idea here is that you initialize the parameters of your model arbitrarily, and you propose new values. And the way you propose new values is through some sort of proposal distribution. So we have some auxiliary distribution that is easy to sample from and work with. A normal distribution will do, something like that. You propose a new value. You evaluate its acceptance. We'll see how to do that in a second. If it's acceptable, we keep it and we add it to our sample. If it's not, we revert to the current value. We actually take another copy of the current value. Then we go back and do it again. We'll propose a new one, given the current value, evaluate it, accept it or reject it, and so on. So in principle, very simple thing to do. How do we accept it? How do we evaluate it? Excuse me. We evaluate it based on the probability of the posterior distribution, the log probability, the joint log probability, under the new value versus what it currently is under the current value. So here's my new value. Does it improve the posterior probability or not? If it does, we always take it. If we don't, we take it with some probability. And that probability is related approximately to the ratio of the probabilities of new versus old. Okay? So if we made things better, we keep it. If we didn't, well, we might keep it. Okay? So we don't always want to move to higher probability. We want to explore the entire distribution, the tails, the peak, and everything. Okay? So we have this acceptance ratio here. So the algorithm, again, just as I said before, have some theta prime, some candidate, generate a uniform random number. If it's less than that ratio, we accept it. Otherwise, we reject it. Okay? In terms of proposal distributions, they can be anything, but you can make choices that make your life harder or easier. The easiest one to implement is something called a random walk proposal, where you pick a symmetric distribution, usually a normal distribution, centered on the current value, and then you sample from it. And so you'll take a jump, you'll accept it or reject it. If you accept it, your next value will, you again, center a normal distribution on that current value, and you take a jump from there. Okay, so it's very easy to implement, right? Or just you're taking centered random deviates and we're adding them iteratively to the current value. Okay. And then an important consideration here is, how wide do we make that proposal distribution, right? If we take big jumps, that has consequences versus taking very little jumps, as we'll see in a second. All right, so I'll pick another, a different but also simple example. This is a linear regression, simple linear regression. So we're trying to estimate the price of houses as a function of age. Okay, so our expected value is a linear function of age. And the error, the sampling distribution is going to be normal. So our expected value will be an intercept plus a slope times the age, and then some value tau will be the standard deviation of that. So there's the data. Oop. New notebook, clear the output. Here we go. All right, so that's what it looks like. Old hoses are bad, apparently. So we're expecting some linear decrease here. I'm not saying this is the best model, this is just a model. All right, and so I'm doing this by hand here, not using PyMC. So what I need is a way of evaluating proposals, right? And I said that the way of doing that is via the joint posterior distribution. So I'm going to take the total posterior on the log scale. Most of you probably know it's easier to work with in logarithms a lot of the time because adding and subtracting are more stable than multiplying and dividing. So these are going to be log normals. I've gone into SciPy stats here and pulled out gamma and normal because those are going to be the distributions I'm going to use. I'm going to put normal priors on the regression parameters, alpha and beta. Or beta naught and beta 1, sorry. I may switch notation on you without warning, just to warn you. And then the prior on the standard deviation is going to be a gamma. And I'm choosing a gamma because it's positive. It's always going to be positive valued, and it can have kind of nice long tails on it as well. So, all right. So here's my prior on the intercept. Here's my prior on the slope. Here's my prior on the standard deviation. I just add them up. And then I calculate mu, and I also add the likelihood given those values of mu and tau. Okay, and so for any given value of the parameters, a, b, and t, and the data, I can calculate the log posterior. And then what my algorithm is going to do, it's just one function here, is it's going to have initial values and initial values of this, for each of the parameters. And one by one, so it's going to be a three-step loop here, one for each parameter. It's going to propose new values for that parameter, accept it or reject it, move on to the next parameter. And so one loop will be going through all three parameter values. So for j in range n params, I do this. This isn't a very general MCMC algorithm here because I've hard-coded, you know, if j is equal to 2, so if it's the standard deviation, I'm only going to propose positive values because I know the standard deviation can't be negative. Insert that value in here, calculate the posterior. Here's the acceptance rate. It's on the log scale, so I'm subtracting and not dividing. There's my uniform random variate. There's what happens if I accept it. There's what happens if I reject it. Okay, so it's pretty straightforward. Okay, I'm going to run this for 5,000 iterations. And I'm going to pick a pretty small proposal variance. So that 0.001 is the standard deviation of the proposal distribution. And I gave away the punchline here by telling you. So the acceptance rate is very high, over 90%, which sounds good. Accepting seems good, doesn't it? We like to be accepted. But it's bad if you're an MCMC algorithm because your proposals look like this, right? So if you pick a really tiny scale parameter for your proposals, it's going to take really tiny little steps, and they'll all get accepted. Everybody will be happy, except it'll take you a really long time to cover the posterior distribution, right? It's not going to, doesn't do a good job of exploring the parameter space. And so it'll look like that, and that's not good. All right, let's make it big then. Let's pick a standard deviation of 20. %, 0.008%, yeah, very small. Also not good. Okay, so what's happening here? Lots of rejections, right? Remember what happens if you don't accept? You make a copy of the current value. So these flat lines are just, it's taking really big jumps way off into the tails of the posterior, and that has a really low acceptance probability. So you want somewhere in between, right? You want to do some exploration, but not all exploration. You do want to characterize the distribution itself. So the key here is to tune it, right? So it's pretty easy here to tune the algorithm to have a scale parameter that is beneficial. What do we tune it to? Well, work has been done to show that for a Metropolis-Hastings algorithm, the optimal acceptance rate is 0.234. So somewhere between 20 and 50% usually works okay. And so that's what we're going to do here. So it's exactly the same algorithm, except I've added some logic in here about so what's going to happen every 100 iterations, we're going to keep track of acceptances and rejections. And if the rate is less than 20%, I'm going to shrink the proposal standard deviation by 10%. And if it's greater than 40%, I'm going to make it bigger by 10%. And so over time, it'll narrow down. So let's run that. So I'm running it for 10,000 iterations, tuning it for 5,000. You don't want to use those tuning values. You actually violate the detailed balance equation when you do this tuning. So we're just using that to set things up, and we'll take the last 5,000. And now we're in business, around 30%, 25 to 30%. And so if we look at these plots, a lot better. This still needs a bit of work, but we're looking for the fuzzy caterpillar. So we're looking for like a homogeneous, we don't want it having any sort of trend associated with it. Stationary, they call it. Okay, that's the kind of thing we're looking for. We'll get into model checking a little bit later. And then again, the nice thing is we can draw from that posterior distribution. So this is a draw of 50 regression lines. So kind of give you an idea of the uncertainty in those regression lines. Okay. That's the idea. All right, so that's sort of to give you an intuition of MCMC. We don't typically use Metropolis algorithms very much anymore. It's not state-of-the-art anymore. The problem with it is it doesn't work very well for most problems. And the reason is that as your models get larger and more interesting, Metropolis Hastings has a really hard time exploring the posterior distribution. The geometry gets too crazy for it. And maybe not unexpected, right? This is a pretty naive random walk algorithm. You shouldn't expect too much from it. It doesn't take much to trip it up. In fact, so this is from a paper from Hoffman and Gelman. This is a complex but simple model. This is I think it's like a 10,000 dimensional multivariate normal. So a multivariate normal with k equals 1,000. We'll say it's 1,000. And these are two arbitrarily chosen marginal values from that. So the truth looks like this, independent, right? It's just a correlated normal distribution. Metropolis Hastings gets you that. Gibbs sampling, which is a slightly more efficient version of Metropolis Hastings, gets you that, which is better, but that's not the same, right? And so you'll get a biased result. So we want a better algorithm. And so what the heck is nuts? This is what we're going to do next. Nuts looks pretty good, doesn't it? That's what we want. So we want a less naive algorithm. And in this case, what that means is we're going to use some information from the model itself to guide our proposals and make them better. 23% is, it's not good, really. It wastes a lot of computation, and it often doesn't get you where you want to go. What we really want to do when we're doing MCMC is explore something called the typical set. And the typical set is, in a model, the area with most of the probability underneath it, which sounds pretty simple, but there's some subtleties associated with it. Most of the probability density is located near the mode, right? It's near the peak. But as you add dimensions, that peak has less and less volume. So as you add, if you think about a section of a line and just some arbitrary piece in the middle, and you turn that line into a square, and that square into a cube, the proportion that's occupied by that centerpiece gets smaller and smaller and smaller until when you have hundreds of parameters, there really isn't any volume left near the middle, near the posterior, near the mean, or the mode. And so it's really hard. You can't just find the middle, find the mode, and start sampling. It doesn't work that way. And so what we're going to do instead is, again, use auxiliary variables, but we're going to use it in a different way. What we're going to do is we're going to explore the form of the posterior distribution by simulating Hamiltonian dynamics. How many people here are physicists? You know all about Hamiltonian dynamics, right? So we're going to essentially treat the posterior distribution like a skateboard park, right? And you're a skateboarder, your point is a skateboarder, and you're going to push the skateboarder down, and what's going to happen, right? She's going to follow the contours of the skateboard park, and at some point, you're going to tell the skateboarder to stop, and that's going to be your new proposal. And then you're going to push the skateboarder again, and they're going to weave around, and then they're going to stop at some point, and that'll be your next point. And so there, you're going to get samples from your posterior distribution, and you're going to go to places with high or low probability by simply climbing gradients. So that's the idea here. So we're going to instead simulate Hamiltonian dynamics. So the Hamiltonian is just this. It's essentially saying that the total energy of your system is just your potential plus your kinetic energy, right? Or your position and your velocity. And so your position will be the point that you're interested in, and the velocity will be just an auxiliary variable that we throw away. Okay? And that's kind of the idea. So what we're doing now is simulating Hamiltonian dynamics. So we're going to change position. Our change of position will change our velocity, and so on. But the hard part here now, right, two hard things. One, the Hamiltonian is a continuous system, and it's hard to do continuous things on computers, right? We've got to discretize this. And then the other things are these derivatives. It's hard to calculate derivatives. Not as hard as integrating, as it turns out, but it's hard to calculate derivatives. But as you know, we have lots of cool software now that does this for us automatically. TensorFlow and Torch and things like that. PyMC uses Theano, or at least it does for the time being, to do this for us. So we built PyMC3 on top of Theano, and it does all of this automatic differentiation for us. So that part of it is easy now. And then what was the other part? Oh, the continuous versus the discretization comes from our algorithm. So this is the algorithm itself is called Hamiltonian Monte Carlo, or hybrid Monte Carlo, it's sometimes called. Created by Radford Neal, really good paper from 1993 if you want to know more about it. And the core of it is the algorithm that does the integration of the Hamiltonian. So what it does is essentially takes a half step for position, takes another half step for velocity, and then another half step for position. So it takes these little half steps and discretizes it. If you take steps, it's kind of like large and small proposals in Metropolis Hastings. If you take really small steps, you'll get a nice, almost continuous line, but it won't be very efficient. If you take really big steps, it doesn't become a very good, your track, your integration isn't very true. So there is some optimization to be done there. And then because we're doing this discretization of a continuous system, we actually do have to do an accept reject at the end. If we were able to do things continuously, we wouldn't have to. But now our acceptance rates are more like 80, 90% rather than 20. Okay, so the HMC algorithm, also relatively simple. Now what we do is we sample a velocity. So how hard are we going to push the skateboarder down the hill or up the hill? Okay, we're going to flick it in one direction. That'll give us some momentum. And then we perform a bunch of these leapfrog steps, and at some point we stop. And we accept or reject that point, and then we do it again. Okay? All right, and so one of the PyMC developers, Colin Carroll, has a nice, it's really hard to illustrate this stuff using PyMC because everything gets kind of black boxed. So I'm going to give you an idea about what some of this stuff looks like. So he's got a package called MCMC that uses a really nice package called Autograd that just does automatic differentiation. And it allows us to track things a little bit. So let's say we have our posterior distribution looks like this. It's a normal mixture of 3 different normal distributions, bivariate normal distributions. So again, relatively simple, but Metropolis would have a really hard time with this. What would happen is it would find one of the peaks and it would just stay there, and it wouldn't be able to jump across those areas of low probability. Okay, and so our leapfrog integration is encoded here in this leapfrog function inside of MiniMC, and all it needs are step sizes and a momentum. And so we're going to do a bunch of leapfrog steps. So we're not doing Hamiltonian Monte Carlo yet. This is just to show you what leapfrog integration looks like. And do 3 different examples. Colin has a really nice blog post that I've listed at the bottom that goes into this stuff. So these are 3 sort of candidate leapfrogs. It's just one. It's just being a skateboarder. It's not doing any sampling. And you can see that it does a little bit of everything, right? You can get it, if you give it a little bit of momentum, it'll just end up and really do a really good job of characterizing one peak. But then you can also move between peaks and so on, right? It doesn't get stuck in the same way that Metropolis would. With Hamiltonian Monte Carlo, we use that leapfrog integration, but we have to do something slightly, a little bit more. What we have to do is we have to decide when to stop, right? You can't just keep skateboarding around forever. We've got to do some sampling. And you don't want those to be either too small or too big. So there's a choice there with how long you wait before you take a sample. And so if we do that, this is going to show 3 different path lengths. And you can see if you choose different path lengths, you end up sampling a little bit differently. In the first one, they're very short, and so they generally stay in one place, whereas path length of 4, it starts moving between the peaks pretty nicely. Okay? All right, that's kind of the idea. Again, this is just skimming over a lot of it. This is hopefully to give you a little bit of an intuition as to how this works. So let's move on to the third one, which is now we're going to get a little bit more into PyMC and how we build models in PyMC and some of the strategies that we'll need for doing that. Okay? So PyMC, what it does is it gives you the building blocks to construct Bayesian models, arbitrary Bayesian models. So you'll sometimes find packages that do very specific kinds of models, like generalized linear models. With PyMC, any model you write down, you should be able to build and fit. And the way that we do that is give you very general building blocks. So there are really 3 different blocks that you need. One are stochastic random variables. As the name implies, they're essentially probability distributions with some other attributes. Deterministic variables, so sometimes we have to combine or transform things to make them fit our problem. And so we have to do these deterministic transformations, and we've got to account for that in the model as well. And then something called a factor potential, which I'll tell you about in just a second. And I'll use, yet again, a different example so you don't get bored. Oh, hold on. Zero outputs. This is a, we use this a lot in PyMC. This is a time series data set of coal mining disasters in the UK. So going back to 1851. So I don't know what merits being labeled a disaster. I guess a collapse of a mine or something like that. And so these are just counts, annual counts of when coal mining disasters happen. And you can see it's an interesting time series because they tend to be higher at the beginning and then lower towards the end. So somewhere in the middle, somewhere in there, maybe something happened, right? There could have been changes in regulations, laws. There could be technological advances. Who knows? And so what we're going to do here is fit what's called a change point model. So the nice thing about being Bayesian is that if there's anything you don't know about the model, even if it's a nuisance parameter, what you do is you put a prior on it and add it to the model and estimate it just like everything else. And so just because we don't know, maybe if you're an expert on the history of coal mining, you can tell me that in 1889 such and such happened, but we don't know that. So it's an unknown to us. So we're going to add it to the model. So we're going to estimate 3 things here. What the mean number of disasters was before a particular point in time that's unknown, the mean afterwards, and then where that change point is. So 3 random quantities.
Chris,
Hi.
are the number of mines constant throughout this time series?
The number of mines?
The number of disasters we had.
Oh, I see. So you think just because we have fewer mines? Yeah, it could be.
But there's World War II and now World War I.
Yes, we're going to assume that they're the same. That's my assumption for today. Yeah, because the rate could stay the same, and we just have a fewer number. Yep. Yeah, you would think there'd be fewer coal mines over time, although maybe not at this time scale. But who knows? Good question. We're going to assume that they're the same, but that will affect what the underlying rate would be. So under that assumption, what we're going to do, what do we have to do? We've got to follow our Bayesian 3-step process. So our probability model, We need a sampling distribution, and we need a priors for things that we don't know. Our sampling distribution I'm going to choose as Poisson. So Poisson distribution is just essentially a model for counts. It's a very simple model. It's got one parameter that characterizes the mean and the variance. So as the mean increases, the variance increases, often used to model counts, although sometimes not very robustly. And then the unknowns are going to be the two rates, before and after, and the change point. So we'll need 3 priors here. So what we're going to say is there's going to be 2 values, lambda 1 and lambda 2, and it's going to be lambda 1 if the year t is less than tau, which is our change point, and lambda 2 otherwise. Okay? And what I'm going to do is put gamma priors on the 2 lambdas because they are rates. They have to be positive, just like we chose a gamma before when we were talking about standard deviation. And then tau is going to just be uniform. Right? I mean, we can see that looking at the data that there's the change point somewhere there in the middle, but we're not supposed to look at the data before we do this, right? Otherwise, that's prior information. But so I'm going to pretend I didn't look at the data and just say that it's uniform. Okay? All right. So how does this get implemented? Well, all these stochastic variables, all the unknowns in your model, will be characterized by a class, an underlying class called free RV. So these are free to vary random variables. And what they essentially are probability distributions tied to, that are able to calculate log probabilities given current parameters. And they're able to draw random samples from them as well. And each free random variable will always be associated with a model. Okay? So they all belong to models. The main way that we create stochastic random variables is using what I would call the automatic method, which means that the probability distribution's already been defined and associated with that free random variable. So we can go in and customize this, but most of the time you're going to do it this way. You're going to say, I need a uniform prior for this random variable, so I'm just going to import uniform from PyMC3 and parameterize it as I need it. So this will create a free random variable object, and it will associate it with this model. All right, and in a similar fashion, we're going to do the same with the exponentials. All right, so we have 3 free random variables. PyMC includes most of the probability distributions that you would want, but it's easy to add custom ones if you need to. I'll show you how to do that in just a second. Some of the important attributes that it will have is a D-type, right? Because you're going to sample, you're going to do things slightly differently if you're a continuous random variable versus a discrete one. It will have default values, so if you don't want to initialize your random variables before you start your MCMC, it will pick the median, mean, or mode depending on what is available to initialize the map. If you just want to use an exponential random variable and not have it associated with a model, it's got a class method called dist that strips away all the PyMC machinery and just gives you an exponential that you can go in and sample from. So I can go in here and go random size equals 1,000, and I'll get 1,000 exponential random variables, not associated with the model. If I did exponential 1, like so, I will get an index error. It says no model on the context stack, right? So it's got to be in a model context for you to use it. But what if you either don't like our implementation of your favorite random variable, or there's a new one, some angular random variable distribution that you want? It's actually pretty easy to add your own. All you have to do is be able to code your own log probability function, and you're in business. So here is a manual version of the uniform log probability. Right? It just takes some value between some lower and upper bound, and returns. You just go to Wikipedia and look up what the probability distribution function is, and you code it up, and that's what it does. I'm returning negative infinity if it's outside the bounds. And then I wrap that in a density dist object, which, as the name implies, is a density distribution, where the log p is your log probability function. And having done that, I can go do all of the things that I would do as if I were using one that came with PyMC. And it's uniform, so the value is always going to be the same, right? That's what uniform means, equal probability. But if I give it a negative number in this case, I'd get my negative inf, which is undefined. Cool? The only things you have to be aware of is that once you get into designing your own probability distributions, you have to know a little bit of Theano. It requires you using Theano functions. The switch statement in here, notice I used the switch method rather than a Python if-else, and that's because that's a Theano function. We've encapsulated a lot of them in our PyMC3 math module so that they're at your fingertips, but you want to be able to code in a little bit in Theano. Okay. The one slight variation on this is, what if you have a random variable that isn't free to vary, i.e. one that you've observed, right? So what's the difference between a normal prior and a normal likelihood? Well, there's no difference, really, except for the fact that you've observed one and you haven't observed the other. So we have what's called an observed RV class. So they're exactly the same. I input a Poisson in this case. The only difference is I use this observed argument to pass the data, and that essentially fixes it at that point. So that is no longer free to vary. So when the MCMC sampler comes along, it skips over you because your value is already known. And again, if I wanted to do one by hand, so here's a good example. If you're anybody who builds survival models, survival likelihoods are slightly more complicated because they have to deal with censoring. And so this is an exponential survival function accounting for censoring, encoded as a PyMC likelihood. Okay? And you can see it has two unknowns, failure and value. So they're just the same, they just have to have this observed value associated with them. So now we have ways of doing stochastic random variables and observed random variables. The next thing are deterministics. So deterministic variables are, the definition here, are ones that are completely determined by their parents. That is, their arguments. So it's a little bit confusing, right? Because if you have a deterministic value in your model and you look at the output from your PyMC run, you'll get a distribution for that, right? Like the log of something. But all of that uncertainty, all of that entire distribution is based on uncertainty that was inherited from its arguments, and it didn't add any itself. Right? So completely determined by parents is really what is going on here. So we have this deterministic class here, and all you do is it's just a wrapper for some deterministic transformation. In our case, the rates are what we need. So it's got to be a switch statement. If it's before this change point, which is unknown, it's one value, otherwise it's another. So here's the switch statement. And there are two ways of doing that. If you're not interested in the values themselves, summarizing them as part of the posterior distribution, you can do what we call anonymous deterministics. These are easier to write, but they won't be tallied as the algorithm runs. There's essentially intermediate values that you're throwing away, and that's the case here. We don't need all 111 copies of two different values, right? We just want the original rates and the change point. So that's the nice thing here, is we don't need to wrap it if we're not interested in it. Otherwise, we want named values. So we just give it a name. If it's got a name, PyMC will keep track of it. And you can always go in and look at what the named variables are. And you can see here that rate is in here, but this one that I did up here that I skipped over, mean of means, is not, because it's an anonymous value. And you can do as many of these deterministics as you want. It doesn't affect your model, right? Because it's just transforming something. There's no cost to it, essentially. The third piece here is what we call factor potentials. These don't get used quite as much. If you don't know about factor potentials, you can probably do most of what you need to do. But occasionally, you need to add something to a model that doesn't quite fit as a stochastic or a deterministic. And these are typically in the form of constraints. These are arbitrary log probability terms that we add into the model. One that's might be relevant here, although in strictly speaking we don't need it for this problem, is what if we want to make sure that the late mean is smaller than the early mean, right? What if we know that a priori? We can do that with a factor potential. And you see, it's not quite a, it's not a random variable, right? And it's not data, really. It's just a constraint. And this could take a variety of forms. So essentially, if we're writing it down, it's like this. It's a indicator function of, the difference. Probably shouldn't be absolute value there. That's not right. Lambda 1 minus lambda 2 greater than 0. And factor potentials are created using the potential object. So all you do is you pass the potential in here, and then the statement now is not a calculated value like a transformation is. This is a log probability. So that's the difference here. Okay? All right, so those are all the pieces that we need to build the model. How do we do our MCMC now? We call the sample function. And that, again, it's a high-level package. And the advantage of that is that it will make reasonable choices on your behalf. But it's easy to customize when it doesn't. So the sample function hides a lot of complexity. The things that you're most interested in is number of draws. How many samples do you want? If you pass it nothing, you can pass no arguments to sample if you want. And if you do, you'll get 500 draws with 500 tuning steps. Usually not enough for me, but sometimes it is. Step implies a step method or an MCMC algorithm. It will do its best to try to pick an appropriate MCMC algorithm, but you're absolutely entitled to go in and override it with your favorite. Information about initialization. We can specify the number of chains we want. So running an MCMC chain is easy to parallelize. It's embarrassingly parallel, so you can run a number of them in parallel at once. By default, in fact, it will give you however many cores you have divided by 2. But you can override that if you want to. Random seeds for if you want reproducible, because this is a random number generator. If you want to be able to exactly reproduce things, you can provide a random seed if you want to. Okay. So, like I said, assigning step methods, you just instantiate the MCMC algorithm that you want. So if you want Metropolis, you can pass it. You can specify different MCMC algorithms to different variables in your model. It's perfectly happy to do slice sampling in one place, a Metropolis in another, an HMC in another. Whether or not it's valid in terms of getting you good results is another question, but it will let you do it. If you don't tell it what to do, this is typically what will happen. If your variable is binary, true, false, 0, 1, we have a binary Metropolis. You can imagine it's not very efficient to use a regular Metropolis algorithm with binary variables. So the binary Metropolis just proposes zeros and ones, and nothing but. Discrete values were assigned to Metropolis. It will know that it'll look at the D type of the variable and only propose discrete values. Otherwise, it will be assigned to this NUTS algorithm that I'm going to talk about in a second, which is an auto-tuned version of Hamiltonian Monte Carlo, essentially. So all those choices we had to make before about leapfrog, step size, and when to stop, those sorts of things. Okay. Starting values. How do we pick starting values? If you don't pass any information to your model, it will choose usually the mean, the mode, or the median. In some cases, what you can do is you can do an optimization. So there's a function called findMap, which finds the maximum a posteriori value for that variable. So it does, it just uses SciPy's optimizers, actually, and finds the mode. So you'll get posterior modes, which usually isn't enough for inference because there's no uncertainty, but you can use that as a starting point. It's not a good thing to do if you're doing Hamiltonian Monte Carlo, though. In fact, we now issue a warning. FindMap should not be used to initialize the NUTS sampler because of that problem I told you before. The mode for large models is not a good place to be because there isn't much probability there. But for small models, it works just fine, like this one here. Okay, so you can always just give it some values, and it will start at those values. And then your samples, when you're finished sampling, sample returns an object called a multi-trace, which stores the trace or the set of sampled values from each of the variables in the model, hence the name multi-trace. So it tells you here that I sampled 2 chains, 500 iterations each, 6 variables. So it's 2 by 500 by 6 in size. By default, those are just given to you as NumPy arrays, but you can specify a SQLite backend or a text backend that will write them, that will serialize them for you. So if you do trace equals SQLite, it will actually slow things down a little bit. One of the best things to do these days, though, if you want to serialize your output, is employ a package called RVs, which is sort of a spin-off project from PyMC3. It was created by some of our developers. It provides an object called an inference data object, which keeps your trace information on the sampling run itself that can be used for diagnostics, posterior predictive values, and so on. And if you've got that, you can save it as a netcdf. And then at a later time, if you need to, reload it, and it's the same thing. Okay, so otherwise, unless you have so many samples with so many variables that you're going to run out of memory during sampling, it's probably best to do things these ways. With Hamiltonian Monte Carlo, you don't actually have to take that many samples because you get a relatively uncorrelated sample. Your effective sample size is quite high. If you're using Metropolis, you often have to get tens or hundreds of thousands of samples because of autocorrelation. Already mentioned parallel sampling. You can specify the number of chains you want and the number of cores. So this will split chains equal 4, cores equals 2. We'll essentially run 2 chains on each core. And then it returns basically n by c samples. I'm not sure why this one's running so slow. Probably because I'm on a Chromebook. And if you're doing multiple chains and you want to assign different values to each of those chains, you can pass a list of dictionaries with those values. So if I want to give a prior value of 0.1 to the early mean on one chain and 10 for the early mean on the other, I can do that. I'm going to stop this one up here. And we typically want more than one chain, and that's why we do parallel by default. Namely, when we're doing convergence diagnostics, some of the diagnostics will rely on having more than one chain because it will compare the values between chains in order to see if your model is converged or not. Step methods, again, these are the MCMC algorithms that are included with PyMC, so Hamiltonian Monte Carlo is one of them. NUTS is sort of the default sampler for continuous variables. So what NUTS does is that it automatically tunes your step size and step number on the fly. So NUTS stands for the no U-turn sampler. So what happens if you follow the Hamiltonian trajectory, what's going to happen if you're on one side of your skateboard park and you run down the hill and up the other side, what happens when you get to the top? You start turning back upon yourself. And so it detects essentially when a U-turn's about to occur, and then it will stop because backtracking is going to be inefficient. And the way that it does that is it employs this binary doubling, so it builds binary trees, and when those trees start to curve back on themselves, that's where it stops, essentially. So this is kind of the idea here, is that it will sample until it starts curving back, until those make a perpendicular angle, and then we'll sample randomly from this chain to get a valid point. Okay. So you don't have to do any manual tuning of step size or path length. Let's see here. Metropolis is in here. Binary Metropolis, as I mentioned, only proposes zeros and ones. There's another sampler that's quite nice for univariate continuous variables, which is a slice sampler, also created by Radford Neal. It sometimes works quite well when Metropolis is inefficient as well, but most of the time we're going to be using nuts. All right, I've got 15 minutes left, which is probably enough to do the last piece here, model checking. Clean up some tabs. Okay. So, model checking is very important. Like I said, particularly with a high-level package, it's very easy to get a result that looks sensible, but may not actually be valid due to any number of reasons. And it generally breaks down into two components. One is convergence diagnostics, and the other is goodness of fit. Convergence diagnostics essentially evaluates whether your MCMC algorithm worked as expected. So has your model converged? So the guarantee that you get, remember back when I talked about having a reversible Markov chain that follows detailed balance? If that's the case, you're guaranteed to converge as n goes to infinity. Well, we don't actually sample infinity, right? We stop at some point, and we want to know, is 1,000 good enough? Is 10,000 good enough? When do we stop? And unfortunately, there isn't a universal answer for that, and so you have to do diagnostics. And the diagnostics that we do are statistical diagnostics. You can't sort of analytically look at a model and a sampler and come up with an estimate of how many samples it's going to take. What we do instead is we use heuristics to look at the sampler and look for essentially evidence. We sort of do an autopsy on it and see if there's any evidence for lack of convergence, right? So it's sort of like null hypotheses. You can't accept them, you can only reject them if there's evidence to reject them. The same thing goes with convergence diagnostics here. And again, if you've got a simple model with 2 or 3 parameters, convergence usually happens very quickly. It's when you get into dozens or hundreds of variables, and then it's a little bit more challenging. As sort of my final example, I'm going to use a rat growth model. This is a little bit more complicated. So these are a set of 30 rats measured, weighed at 1-week intervals starting at week 8. So there's 8, 15, 22, 29, and 36. And we essentially model the growth curve, essentially. And so they kind of look like this. And so I'm just going to fit a linear model here, but I'm going to use a hierarchical model. And this is one of the motivations for doing Bayesian analysis, is it makes hierarchical models really easy to do. What do I mean by hierarchical? I mean that some parameters themselves have their own models, right? So what we're going to do is, rather than just say there's one growth rate or one intercept to the model, we're going to say that there's a population of them, and each rat, rather than having either a single value or entirely independent values, we're going to say that they're drawn from a population of rat weights and rat growth rates, rat weights and rat growth rates, to kind of model this variation, okay? So the model looks like this. It'll be, the weight is a linear model, but you notice that alphas and the betas are subscripted here. So each rat's intercept and slope is drawn from a normal distribution with some population mean and standard deviation for both, okay? All right, so here's the model. There are the hierarchical means, there are the hierarchical standard deviations. And now you can see these normals aren't priors, these are models of the variation in initial weight and growth rate. And then we calculate an expected value, so each rat gets its own values indexed, and then our likelihood function is normal. A cool feature of PyMC3 is that you can actually print out the model itself in the form of a directed acyclic graph. So all Bayesian models can be expressed as directed acyclic graphs. So this shows, your data is shaded in gray. It's an observed stochastic. All the other ovals are stochastics, and then it's got these plates showing that there are 150 data points, hi Slack, and 30 rats. So you can kind of quickly validate whether or not your model is specified as you expected it. If you've got some node that's floating off into space, you've made a mistake somewhere. All right, we're going to run this model. We're going to start looking at some of the output. While this is running, I'll start talking about them. So there are a range of ways of doing this. The first step is always just look at the output. Just like the first step in any data analysis is just look at the data, plot the data. You want to inspect your traces and your histograms, plotting them. And so this is where the RVs package comes into play. So PyMC has a lot of diagnostic and plotting functions, but a lot of them have been spun out into RVs. And in fact, now we just call RVs from PyMC. So here we go. So these are the estimates of the means for the slope and standard deviation. And we have a nice, essentially relatively homogeneous trace. It's not trending in any way. The variation isn't changing over time, and we have nice, neat, symmetric KDEs for or histograms over here as well. So always the first step, just to see what it looks like. I'm going to intentionally create some ugly ones here, so you can sabotage your MCMC runs by giving it really bad starting values and really bad samplers. So here I'm going to start the mean at 1,000, mean intercept at 1,000 and the mean slope at -10. And when you do that, you get, stuff like this. And so you can see when you have two chains and they're not doing exactly the same thing, that's a problem. It's a little bit hard to see, sorry, but when you get any of those diagnostic patterns that we saw when I was demonstrating Metropolis Hastings, either the snaking around the parameter space or long periods of rejection, that's also going to be bad. And in fact, one of the ways that you can help diagnose this stuff is to deliberately start separate chains at varying starting positions. And what you're looking for is ergodicity. It has an ergodic behavior where it will, regardless of where you start it, will eventually find its way to the same spot. So that's a good sign there. And these would be tuning steps, samples that you would throw away anyhow. There are a few formal methods for doing diagnostics. One of the key ones is the Gelman-Rubin diagnostic. And what this does essentially is a formalized way of this. What it does is essentially an analysis of variance of several chains. And the idea is that if a model is converged, the variation between chains should be about the same as the variation within chains. You shouldn't really be able to tell them apart. Early in the sampling here, you can see the between chain variance is much higher than the within chain. So it calculates this factor called the potential scale reduction factor, this guy here. So it's essentially the ratio of the overall variance over the within chain variance. And over time, the between chain variance should go away. So as n gets large, n being the number of samples, this goes away, and it's just W versus, so those should be approximately 1. So you're looking for what they call R hat values of near 1. And so you can calculate that, pull in the R hat from RVs and calculate them. You can see in here, most of these are around 1. You start worrying if it's, 0.8 or less, something like that. And in fact, if you plot some of so there's a forest plot forest function. They're really good for visualizing posteriors of lots of variables in the same figure. So these are posterior plots of the standard deviation of the slope and intercept. And if you say R hat equals true, it will plot the R hat values for you. Okay, and you can see both of these are close to 1. Okay. Autocorrelation is another nice diagnostic. Autocorrelation isn't always a huge deal. And you can expect some autocorrelation because these are, after all, Markov chains. They're dependent samples. But you do want to minimize it because what it will do is essentially reduce, if you have a high level of autocorrelation, it reduces the independence between draws, and essentially your effective sample size goes down. So you have to draw more samples to get the same level of precision from your estimates. So you can plot an autocorrelation function to look at this. So these are two plots of MA, and actually same plot of MA, one for each chain. And you can see here each value on the X is a lag. So the first notch is the lag between a one-step lag, a two-step lag, and so on, all the way out to 100. And so it should look like this, sort of random, small amounts of random variation. What you're looking to avoid are things like this. So here we have, particularly in the second chain, a high level of autocorrelation all the way up to lag 20 or 30. And it typically means you got to reparameterize your model. You don't have a very efficient parameterization, or better tune your model. And yeah, the main consequence to this is that you will have a lower effective sample size. So here's effective sample size, which is a function of the number of draws that you take and the number of chains. But you can see here's the autocorrelation summed over all of the lags. And if that's really high, it lowers the effective sample size. And you can similarly make a forest plot with ESS equals true. So effective sample size equals true. And it will plot ESS instead of R hat. So in this case, I drew 2,000 samples after burn-in, and you can see for these two parameters, it was pretty close to 2,000. But for the standard deviation, we had an effective sample size that was only about half. So we did have some autocorrelation. There's a temptation, if you read some early MCMC literature and certainly papers people publish, they'll thin their sample. They'll just take every 10th draw. But there's really no point in doing that because what are you doing there? You're reducing your sample size by a factor of 10 or whatever. So just leave it alone and show your autocorrelation. The effect will be the same. So I've only got a couple minutes left. The only section that I haven't been able to get to is the gradient-based sampler diagnostics. I'll just let you do that, on your own. It's just a different set of diagnostics that uses a little bit more information because of the fact that we had gradient information. So you can actually do a better job of diagnosing gradient-based sampling than just Metropolis Hastings. So I'll stop there, and I probably have 2 or 3 minutes left for questions, and I'm happy to answer everyone's questions during the weekend if you can track me down. So let's wrap it up there. Thanks a lot for attending and hanging in for the whole hour and a half. Maybe one question, one or two? Yeah. What is trace? No, it isn't. So the question was, what is a trace? A trace is just MCMC lingo for the sample. So it's the time series of sampled values, and it's just called a trace. Yeah, it's not the same as the trace of a matrix, absolutely. Thanks for clarifying. Well, so the question had to do, how do you make the transition from dealing with classical statistics, namely likelihoods, into Bayes? Machine learning. Oh, I see. So maximization. You're right. So here the benefit you're getting is dealing with uncertainty, and you're getting probabilistic, on a probabilistic approach. The cost to that is specifying priors, right? So that's really the only difference, right, is you specify priors for your unknowns, and that allows you to get probabilities in and probabilities out. And that's the thing that you kind of have to, it's more of the art, right? You learn what priors tend to work and which ones don't. And so it often takes practice. But, the guideline is to, understand what your variables are, what values they can take, and sort of practice. So you can make Bayesian versions of traditional machine learning models, right? There's Bayesian neural networks, and what is that? That's just putting priors on the weights between the layers. So there's actually a nice example in the PyMC repository of a Bayesian neural network. And so looking at models like that that are just Bayesian versions of things you're familiar with would be the best way to get started. All right, thanks everybody.